Good evening, everyone. I am Subhash, roll number 2023104, and today I will be presenting our project titled Multi Pipeline ETL and Reporting Framework for Web Server Log Analytics. So, the main goal of this project is to process the NASA HTTP logs using four different execution pipelines: the Apache Pig, Java MapReduce, MongoDB, and Apache Hive. So the main part of this project is that all four of these pipelines process the same raw data set, use the exact same logical parsing rules, support the same batching semantics, and execute the same analytical queries. And finally, load these results into a common relational reporting layer. So this is not just four separate scripts running; it is one unified ETL and reporting framework. The input data is raw web server logs, and these logs are semi-structured text records and not clean tables. Each records contain fields like host, timestamp, HTTP method, resource path, protocol, status code, and bytes transfer. Challenge is that the dataset also contains malformed or incomplete records. And so before analysis, each pipeline must perform proper ETL. That includes first ingesting, then parsing, validation, cleaning, batching, and then aggregation. Our system is designed so that this ETL work happens inside the selected pipeline itself. For example, if MapReduce is selected, parsing and cleaning happen inside the MapReduce code itself. If Hive is selected, the same thing. It happens inside Hive itself. This is as you would want it to be, and according to the guidelines, as you would want each pipeline to be responsible for its own parsing. Then now we will look at the different queries that we are expected to handle. So query one is daily traffic summary. So now it groups requests by date and status code and computes the request count and total bytes. Query two is top requested resources. It identifies the most requested resource and also computes total bytes and distinct host counts. Query 3 is hourly error analysis. It focuses on HTTP status codes between 400 and 595 and computes hourly error count, total request count, error rate, and distinct error hosts. Since there are three queries and all three have to be implemented across four pipelines, the system supports 12 execution combinations. Now we will go into the common parsing strategy that we're using across all the pipelines. I'll go into the code just to show as to how that looks. So here is the regex used in the MongoDB pipeline to analyze each record. The regular expression here extracts host, timestamp, method, resource path, protocol, status code, and bytes. This is important because if each pipeline pass logs differently, then the final result would not be comparable. So the parsing logic is aligned across MongoDB, MapReduce, Pig, and Hive. So here is how it looks in the MapReduce code. Yeah, as you can see, it's the exact same regex used, which indicates that it will, in fact, be the same malform count that we get at the end, which will be showed in the demo later on. So now, moving on to the timestamp and field normalization. So this section will show the parsing and timestamp transformation logic, especially in MongoDB. So just give me a second to bring up the code. Yeah. So as you can see, the timestamp is passed through another regex, and then everywhere we try to access a field and we do not get a value, we return null. This is important because we want to keep a track of the malformed records. So the log line parser converts the raw line into a structured record and handles the byte fields. In weblog, sometimes the bytes field is just a dash. In our implementation, this is treated as 0 bytes. If any important field is missing or valid, the function returns null. This means the record is treated as malformed. Although this is just the code for the MongoDB pipeline, the same logic rules are used everywhere. Now, moving on to the malformed record handling. I'll show that in the MapReduce code so that it becomes easier. Just a second for me to pull that up. Yeah, so here, yeah, yeah. This is the mapper and this is the reducer. So the time window mapper and the time window reducer. So malformed records should not be silently ignored. If parsing fails, the record should be counted as malformed and linked to the current batch. In MongoDB, malformed counts are tracked while streaming the file. In MapReduce, malformed rows are emitted with a special prefix so that they can be included in the metadata output. This is useful because ETL pipelines should not only produce final analytics, they should also expose data quality information. In our database, the malformed information is stored in tables, malformed record summary, and each malformed record in the malformed records table. This makes the system more transparent and easier to debug. Now, moving on to the batching strategy. Let me pull up that code. Yeah. In the time window mapper, so here we look at the batching strategy. Batching is implemented to organize execution and capture batch level metadata. For our demonstration, the main batching mode is calendar month batching. Since the dataset contains July and August logs, the natural batch interpretation is July records as one batch and August records as another batch. But the code is very modular. Any other month that could appear in the logs will also be considered as a separate batch. The MongoDB pipeline creates a calendar month batch assigner. While reading each line, it assigns a batch ID based on the past log date. In MapReduce, the time window mapper calculates the month offset from the first observed month. This allows MapReduce to assign batch IDs using the same calendar month logic, as can be seen here in this part of the code, where basically we note down the first year that was seen in the in the logs in the first month. This kind of gives a nice month like batch ID that you can assign to each new month that is being discovered in the log files. So now moving on to so far I've explained the common design, raw log ingestion, common parsing, timestamp normalization, and malformed record tracking. And now the batching was also been explained. Uh, Now we will be moving on to Satish, who will explain how each of these four pipelines implements this ETL and query logic using its own processing model. Yeah, thank you.
I am Satish, IMD 2023-030, and I'll explain all the pipelines. So let me just start with the pig pipeline. So the pig runner first creates a run specific HTTPS directory under slash dem slash NASA ETL slash pig. So then it uploads the raw log file into HTTPS using the HTTPS DFS put command. Um, so, so after that, it dynamically builds a combined pig script. The combined pig script includes common.pig that is for parsing, cleaning, and batching. The metadata.pig for batch and malform record metadata, and the selected query scripts. So let me just show the common.pig. So in common.pig, raw lines are loaded using text loader. So each line is parsed using Python UDF. Then the relation is split into valid and malformed records. The batch ID is calculated inside Pig itself. For calendar month batching, it uses the parsed year and month to assign batch IDs. So Pig performs a complete ETL flow, that is loading, parsing, validation, batching, aggregation, and output generation. So next, let me just show the MapReduce pipeline. So we just go to the code. So this MapReduce pipeline is implemented in Java. The parse log line method performs the same parsing and validation logic that Subhash described. It extracts the fields, validates timestamps and month values, converts bytes, and returns null, and the record is malformed. So this is the same that Subhash had explained before. So let me just go to the other part. So these lines implement the metadata reducer. So then the MapReduce pipeline runs the metadata and batch assignment phase. Um, so the batch metadata reducer, so this one, assigns each line to a batch. It tracks the record, so it tracks the records processed, malformed records, valid parse records, and malformed raw lines. So valid records are emitted with a v slash valid records are emitted with a v slash batch ID prefix. Malformed records are emitted with that is yeah the malformed records are emitted with m slash batch ID prefix. Batch summary rows are emitted with b slash batch ID prefix. So that is given over here. So this design lets the later MapReduce jobs consume already batch assigned structured records. Let me just go to the other part of the code. Um, so then the driver launches query jobs. For example, query one creates the daily traffic job. This job groups by date and status code and computes request count and bytes total. So that is given over here. So the MapReduce pipeline is the most low-level implementation because we explicitly control mapper, reducer, keys, values, counters, and output loading. So next, let me just explain the Mongo pipeline. Let me just go to the code. Yeah. Um, so the MongoDB pipeline is implemented in Node.js. So it opens two connections. One is to the MongoDB, which is used as the processing store, and the other one is Postgres, which is used as the final reporting database. So these lines show the streaming record processing loop and batch assignment. The pipeline streams the input log files line by line. Valid path records are inserted as structured documents. So let me just go to the. So this section contains the aggregation logic for the analytical queries. Um, the MongoDB aggregation pipelines are used to compute the three queries. For query one, the MongoDB groups by log date and status code. Um, so for query two, it groups by resource path, count request, sums byte, and computes distinct hosts. For query 3, it groups by date and hour, counts total requests, and conditionally counts the status code between 400 and 599 as errors. So this shows the document store approach to ETL and analytics. So next, let me explain the Hive pipeline. So the Hive pipeline uses Hive QL scripts. So the runner stages. So yeah. So the runner stages raw logs into HDFS, creates a run-specific Hive database, and then executes a sequence of scripts. So in this setup.hql script, Hive creates an external Hive creates an external table over the raw HTML input. Then it uses the regex extract to extract the same fields as other pipelines. Um, so this section performs the validation, creates clean structured data set. So the validation step checks whether host is present, method is present, resource path is present, protocol is present, and etc. So after validation, Hive creates a structured clean data set. So these files contain the final analytical queries. So the query scripts are concise because Hive query is declarative. So query one groups by date and status code. Query two groups by resource path and count distinct hosts. Query three groups by date and hour and computes error rate. So Hive represents the data warehouse style of processing. So Hive and Pig write their outputs into HDFS directories. Their runners then merge those HDFS part files into local TSD files. Let me just go to the scripts here. So this section creates schemas. So this section creates schema objects and temporary loading tables. After that, both pipelines call the shared loader. So that is, they call this particular script. So these lines perform the final inserts and the common reporting tables and update metadata. So this script creates temporary Postgres tables, copies TS3 outputs into them, and then inserts the final records into the common reporting schema. MapReduce and MongoDB load results into Postgres directly from their own code. So all four pipelines eventually produce the same final reporting structure, even though their internal execution models are different. Now Gaurav will demonstrate the overall system and show the UI and the working and comparison of different approaches. Thank you.
Far, we have discussed the ETL architecture and the internal implementation of the four different pipelines. I'll demonstrate how the complete system works from the user perspective and how we compare the execution in terms of runtime for the four different varieties of pipelines. So let me first explain the front-end interface. So this front-end interface acts as a centralized controller for the entire ETL framework. On the left side, we can select the execution backend that we want to run. So the framework supports the four different processing methods, which is Apache Pig, Hadoop MapReduce, MongoDB, and Apache Hive. Even though these systems internally process data very differently, the user interacts with all of them through the same workflow. So here, the user can provide the log files paths for which the user wants to run the pipeline for. So I'll be using the NASA access log for the month of August and July. So we can execute either a single query or all the queries here. The user is given the option to do so. For the batching configuration, currently we have given an option to run it either 1 week as a batch or 1 month as a batch. So I'll go with 1 month. That means July and August will be treated as separate logical batches during processing, and after all the batches complete, it provides like I can choose a global aggregate or per batch analysis. So I first go with the pig pipeline. So the user runs the pig pipeline. So once the run starts, the front end sends the configuration to our fast API based backend. So the backend generates a unique UUID, which stores this UUID is unique and it stores the execution metadata in the PostgreSQL database, and it starts the selected pipeline. At the same time, the terminal section as visible here is streaming the live execution logs from the backend. So while this is running, the front end itself does not really change based on the pipeline. It's just the logs and the backend method in the selected pipeline way with changes. So whether we are using Pig, MapReduce, MongoDB, or Hive, the orchestration layer remains identical. So now while this is executing, let me briefly explain what's happening internally. So the pipeline performs ingestion of the raw NASA logs, the parsing and validation is performed, and then all the malformed records are filtered. And we also keep track of the record count of such malformed records, and this metadata is also stored in the PostgreSQL database. And then batch level processing starts, and different analytical queries are executed, and the final results are again loaded back into the PostgreSQL database. So we can see that the output is stored, and also the pipeline completed successfully, and the results for all the queries are stored in the PostgreSQL database. So here in the results tab, we can so in the results tab we can immediately see the execution level statistics such as total records processed, which is 3 lakh, I mean 34 lakh 61,613, and the total number of batches here, which is 2, as each batch is for a month. As we are doing, our batching strategy is to use 1 month as one batch. We can see the runtime for the execution, the number of malformed records, the aggregation method that we use, whether it was per batch or global, and the average batch size across runs. So this is important because the framework is not only generating the analytical results, but it is also keeping track of the execution metadata for comparison purposes. So we can see the batch metadata section. So for each batch, the system assigns a batch ID, in this case 1 and 2, and the number of records processed in each batch, and the number of malformed records, as well as the execution timestamps, as in when the particular batch started running and when it completed. So since we are using calendar month based batching, in our case, July and August are treated as separate logical batches. So the malformed record tracking is very useful because real world log datasets are not always perfectly clean. So we are removing records which contain invalid timestamps, malformed request fields, missing status codes, or if some parsing failure happens. So instead of just directly dropping these rows, we store them separately. So the system records and stores the malformed record counts with in while keeping track of the batch ID as well as the reason for the failure. Validated records are participating in these analytical queries. So let me explain the three outputs generated by Pig. So the first query is the daily traffic summary. So this computes the request counts, the transferred bytes, and the status code wise aggregation group by date. So this is the output. So now the second query is the top requested resources. So this identifies the most frequently accessed resources along with their count, the total number of bytes, and the number of distinct hosts that are calling them. So this is the output. So now the third query is early error analysis. So this computes early error counts, the total number of requests, the error rates, and distinct hosts which are generating these errors. So an important design decision here is that all four pipelines write into the same Postgres database, which has the same reporting schema. So although there are four execution engines which differ internally, but their outputs become directly comparable. So now let me briefly show the schema. So we have a table called ETL runs. So this table stores the pipeline name, the run UUID which was assigned and which is unique. So it acts as a primary key. We also have batch mode, whether it's a weekly or monthly method, the aggregation mode, whether global or per batch. We keep track of the malformed record count for that particular run and the total number of records and other execution status, like whether it's still running, completed, failed, and when it started, when it completed. Then we have different metadata tables such as batch metadata, malformed record summary, and malformed records. So these help us to keep track of the different malformed records related information. So the analytical query outputs are stored in per query tables like daily traffic, top resources, and early errors. So this centralized reporting layer, like a database where all pipelines are storing this output, enables us to compare the runtimes across the different pipelines. So MapReduce. So now I'll be running the MapReduce pipeline. So again, to maintain uniformity, I'm choosing both the NASA logs and running it over all the queries, and a batch to be of 1 month size. So as you can see from the logs, all our MapReduce jobs are reading and writing data into the Hadoop file system. So the MapReduce job was completed. As you can see, the runtime here was 121.89 seconds, and we've got the same count of malformed records across both the batches when compared to Pig. Like here also in Pig, we have the same number of malformed records in each of those logs. So we are ensuring consistency over different pipelines by having the same parsing logic for all the pipelines. And each pipeline runs the parser on its own and not as a global parser. So these are the results. So now I'll choose the MongoDB configuration and run the same So similarly, MongoDB also completed with a runtime of 168.92 seconds. Again, we have the same malform count across both the batches, showing that we use the same path and logic across pipelines. Uh, in the MongoDB pipeline, the parse log entries are stored as documents, and analytics are computed using MongoDB aggregation stages such as match, group, project, sort, and limit. So now for Hive, I'll just demonstrate execution only on 1 month dataset to show that it works on all variations. So I'll choose one query and the pipeline to be Hive to show that it works with that. So the Hive pipeline also completed for 1 month, as which was August. We had a milestone count of 2046 before as well. So it took a 200-second runtime on 1 month log only. So Hive introduces a lot of overhead when compared to the other pipelines. So overall, the runtime analysis that we got was MongoDB performed much efficient than MapReduce before Hive. Second was MapReduce, and it was a lower level and optimized version when compared to Pig and Hive. So third was Pig, and last was Hive. We also have indexes present on different tables to optimize the performance. So this was our demo. Thank you.
So now let me just explain all the pipeline. So I'll start with the pick pipeline.